Number 24, strong versus weak bases. I'm going to use a symmetric ketone first, and then the next number would be asymmetric ketones. A strong base like lithium diisopropylamide will completely convert the ketone to the enolate in nearly 100% yield. So you get all of that, and then if you add an electrophile in as part of your next step, you'll get one product in pretty good yield. The problem comes when you start using a weak base like OH-. It'll come in and it'll pull up one of your alpha hydrogens, but it'll only do that to like a very small percentage of the ketones in the reaction vessel. So you get the enolate, it reacts with the Br, and you get the product. But then you have a bunch of stuff in the reaction vessel, and the product you made still has alpha hydrogens that can be pulled off. So you end up with the whole thing kind of expanding, and you're getting multiple products. It'll give you basically every combination of that, to the point that you're adding that, if you have the alkyl halide in excess, you're adding that alkyl chain to everywhere you can, in place of every alpha hydrogen. When you have asymmetric ketones, there are two options really. On the left side, there are two alpha hydrogens you could pull off to get you this guy right here. And then on the right side, there's one to pull off to get you that guy. And then if either of those react with the same alkyl halide, you get totally different products. Product A is favored by cold temperatures, negative 78 degrees Celsius, or bulky bases like LDA. And B is favored by heat or normal temperatures and a smaller base like KH or OH-. There's a pretty good way of actually forcing the A product if you don't want to cool it down that low. And that is, you react it with this guy right here, two methyl groups on a nitrogen attached to an NH2. The NH2 behaves like the NH2s we've seen previously, replacing the O with the double bond. Then butyllithium, as a bulky base, will attack that lone pair on the upper nitrogen, but it will choose the less sterically hindered side. The lithium will, to complex with it. And then the butyl part, the base, will pull off a hydrogen from the less sterically hindered side, giving you that. You react it with your alkyl halide, and then you use acid to return your nitrogen complex back to its original ketone form. Acid's good for returning that sort of double bond whatever back to its original state. We're going to talk a little bit about the Michael addition. It involves two compounds. The reaction of an alpha-beta unsaturated carbonyl, or this guy, with an enolate ion as the nucleophile, or this guy. So first you have to make your enolate ion nucleophile by pulling it off using a base. And then you have to have this. And this guy can react, as we saw above, via conjugate addition. When something attacks the beta carbon, the nucleophile attacks the beta carbon, and that's what we're using here. Or direct addition, which is what happens with Grignards or H+ sources, which we saw right there. So in this, you take that nucleophile that you made and attack the alpha-beta unsaturated ketone via conjugate addition. It creates the enolate, which then collapses and protonates. And that's it. That's your Michael addition. Next is the Stork-enamine reaction. It starts with a version of enamine formation that we saw above. So, in 21, you can rewind the video. But let's see if I can find it. Right there. But this is just the enamine is cyclic. Not a big deal. Then the enamine reacts via conjugate addition, just like what happened to the Michael addition. And you get, this compound, which is good if you want that compound. I know that sounds ridiculous, but it's just something to remember. Next, easy peasy, aldol condensation. This, on any standardized exam, the tip is you'll see an aldehyde or a ketone with a little number 2 next to it, meaning there are 2 equivalents of it, and you'll see some sort of base. Regular old aldol condensation, you'll probably use OH minus as your base. So first step, OH minus pulls off an alpha carbon. I know, shocking. Then in the next step, line up another molecule of your starting material, sort of mirror image beneath it, and the enolate collapses and kicks that double bond into the only thing that could possibly act as an electrophile. Then it creates this molecule, which then protonates to give you an alcohol, or a beta hydroxyaldehyde, as they're called. You could leave it there, but what's normally done is an acid workup. What happens in the acid workup is it's dehydrated using an acid catalyst. So you protonate the alcohol into a good leaving group, and then pull off that hydrogen, and you end up laying down a double bond. You can also catalyze this with a base that's known as the E1CB reaction, but like most other times where you're just dehydrating or hydrolyzing, you can use either. Now we're going to look at the crossed aldol condensation. It's really not that hard. You have to control it because you've got 2 different molecules and you don't want your base to go willy-nilly and decide which aldehyde to react with. So there are 2 approaches you can take to this. On standardized tests, you might see they might make it easy for you and give you a normal aldehyde and also an aldehyde that doesn't have any alpha hydrogens, which is a tip-off right there. If, say, your carbonyl carbon is attached directly to a benzene ring, then you know which alpha hydrogens to take off, obviously. Another way of doing it, if you're in the lab and you want to just force this reaction right here, is to only put one of your aldehydes in the reaction vessel and react it with LDA completely to get as much of that enolate as you can, and then slowly titrate in your second aldehyde to get mostly this in acidic workup. Also watch out, because we'll see this a little bit later when I talk about the Robinson annihilation, but you can, if you have 1,4 or 1,6 diketones, you can form 5 and 6 membered rings. With this and other diketones as well. Watch out for essentially intramolecular examples of this sort of thing. A Claisen condensation being like a general word for takes 2 carbon-containing compounds and clips them together, is a condensation involving esters. So one thing to note, an ester has a leaving group, which is the OCH2CH3 in this case. Use O minus CH2CH3 as your base, because this looks a lot like transesterification. And you want to create a situation where if your compound accidentally undergoes transesterification, you create the same ester you started with, so it doesn't matter. So the only thing that it can do to actually change up what you have is clip off that hydrogen, which will fall in, making your enolate. And then it reacts with another version of itself. Now, here we just saw alcohols being formed because there was no leaving group there. Now that we have a leaving group there, we can form and collapse the tetrahedral intermediate and kick off the leaving group, giving you this guy. I know, pretty sweet, right? So that's the Claisen condensation. Crossed Claisen condensation. I know, it just gets better, right? It's just when you use two different esters. This one might not be as easy to control with LDA. And again, on a standardized test, you'll probably see something with no alpha hydrogens being used to give you a predictable product. You can do it intramolecularly. It's known as a Dykman condensation or Dykman condensation. I'm not actually sure about the pronunciation. But so you see this guy right here. You pull off the alpha hydrogen, attacks the carbonyl, forms, collapses, kicks off the ester. Yeah. Right as rain. Other similar condensations that don't really fit into either aldol or Claisen. A ketone and an ester makes a beta diketone. Ketone, ester, yeah, that's a condensation. A ketone and a formate ester makes a beta ketoaldehyde. And a ketone and diethyl carbonate makes a beta ketoester. This is the Robinson annulation. It's 1 part Michael addition, 1 part aldol condensation. In the first, you have an alpha beta unsaturated ketone and a ketone, which are the and in basic conditions, which are the ingredients of a Michael addition. So you tear off this alpha hydrogen there, or this one in this case, and that attacks right there. And this molecule is turning around, blah, blah, and then that protonates, and it gives you this guy right here. Now, you have 2 ketones, and you do an aldol. So say you tear off that alpha hydrogen, and it attacks there, kicking that into an alcohol, which then eliminates. That's the Robinson annulation. The driving force behind this is the preference for 6-membered rings. Decarboxylation you're going to see a lot, and especially in biochemistry with pyruvate and pyruvic acid and things like that. Take this base, clip off that, and it sends that bond flying in there to make carbon dioxide. So this bond clips off and it goes there, kicking that up. So you get your enolate and your CO2. The enolate has a resonance form. And that's it for reactions of carbonyl compounds. I'm going to go try to edit these together.